Okay, welcome to note set 6 in our third unit on effects in our digital audio signal processing course. I say effects, but we're talking about amps as well. And so that's what we're going to be focusing on here, guitar amplifiers, although the ideas we're going to talk about in this note set are applicable to effects as well. And let's look at the title of this note set, black box modeling. So we know what that means. That means that we don't have a schematic to this, or we're reluctant or unwilling or don't know how to deal with using the schematic. But we have a physical thing that we can plop down in the lab, and we can make some measurements of this. And then the idea is to use those measurements to try to figure out how to emulate or model the thing that we just measured. And we're also focusing only on the linear parts of nonlinear effects. So maybe we can get inside the box and isolate, okay, from this point to this point is just a linear circuit. And we'd like to figure out how to mimic that, how to model that circuit, even though there are nonlinear parts of the circuit elsewhere. So that's the idea. And a little bit of a reading here, just a few pages of this longer paper that's a nice review paper. To be honest, those few pages don't really cover the technical stuff that I have in this note set. They just kind of set the stage for it. So I kind of figured we'd go into a little bit more detail, and I'd show you some of the DSP tricks that we can use to try to figure out how to model linear circuits. So we're going to be mostly focused on tube amps and distortion effects boxes, but just the linear part of those. So as we've seen, there are linear stages in amplifiers and in effects. So here's another new or a different amp than what I've showed you before. I've been showing you the Fender Tweed Princeton. This is the Fender Tweed Bassman. 5F6A is the model number, if you know those things. This was only produced for about 3 years, but it is one of the most famous Fender amplifiers. In fact, it is this Tweed Bassman that was the motivation for Jim Marshall to create his very first Marshall amplifier. In fact, he pretty much just took the Bassman and mimicked it with components that he could find in England, where he was living. But back to this. So I forget where I got this schematic from. They're littered all over the internet. You can find schematics for all these old amplifiers. I should have referenced where I found this. But right here is the tone control, and that's called the tone stack, because if you look at this, there's like a stack of R's and C's. So that's why it's called a tone stack. So suppose we want to model just that. We've got things going on for everything else. We've got the tubes here, the tubes here, the tubes here, and the tubes here. We've got models for that, and we've got models for everything else. Your job, maybe you're working at a company like Line 6 or Yamaha or somebody like that. Your job has been given to you. Find a way to model that. Now, there's a variety of different ways that we could go about doing that. You could try to find out what the frequency response of that circuit is by doing circuit analysis on it. And people have done that, and it's not too hard. It's maybe a little tedious, but not too hard to do. But maybe you've been told, don't do that. You have an actual Bassman in the lab. Wow, that'd be great. Go and plug in and play it. You've got one. We should measure it just to make sure that we're capturing all the essence of that somehow. So that's what we're going to do. Or maybe you are trying to model this linear circuit part, the tone control part of the Boss DS1 distortion. So maybe that's your job at line 6 or Yamaha or somebody like that. So how do we do that? Now we notice that these filters pretty much consist of resistors and capacitors. There are inductors in amps, but so there's one right there, but they're mainly in the power supplies. They're not doing filtering. So R's and C's, and there's just a few of them, right? 3 capacitors, a handful of resistors. Here we have just a couple capacitors. So we know that the number of capacitors is going to correspond to the order of the filter. So these are going to be pretty low order filters. So keeping that in mind, we should be able to come up with a fairly low order digital filter that will mimic those. Okay, so black box and gray box. So remember, black box, we don't use any knowledge of what's in there. And gray box, we say, all right, we might not know, or we're not willing to use the exact schematic to figure it out, but we have some idea. So we just did a gray box kind of thing. Oh, look, there's just a handful of capacitors in there, so we should have a low order filter, right? Now, we've already learned how to measure the impulse response, or equivalently the frequency response of a linear system. So you shove in a swept sinusoid, whether linearly swept sinusoid or exponentially swept sinusoid. If the thing you're measuring is purely linear, either of those will work fine. But there might be some residual minor nonlinearities, so the exponentially swept sinusoid might be a better idea. So if you're not sure what I'm talking about, go back to the note set on that in Unit 1. So we've measured that. We have the impulse response. That's what we're going to focus on, having the impulse response, because that's the easiest, most direct thing to measure. From those measurements, we'd like to design some discrete time IIR filter, because analog filters are more likely to be similar to IIR filters than FIR filters. And we want to do that so that this IIR filter will mimic the original one. And again, we're focusing on a low order system. Okay, so a true black box approach, we have no idea what's in there. We might just take this impulse response and say that is it. We're going to treat it as the impulse response of some FIR filter. Now that impulse response might be very long, which leads to a very long FIR filter, and that's going to have some complexity issues. Plus, what do we do about knob settings, right? We're going to measure this here. There's a knob right there that's controlling the bass, and there's a knob, the mid-range, and a bass knob and a treble knob. So we've got 3 knobs. What that circuit does is going to be a little bit different, or the impulse response is going to be a little bit different each time there is a change in the knobs. So that means we're going to have this long FIR for impulse response for every different knob setting. And it's going to be hard to interpolate between those, because a slight tweak of a knob is going to change a particular FIR coefficient perhaps quite a lot. So that's a challenge. Gray box approach says, well, we might not have access to the actual schematic, or we're not willing to fully commit to using that schematic, but instead we know, like we just said, look, it's a low order thing. So we know it's a low order system, and we should be able to come up with some low order discrete time IIR system that will approximate the measured impulse response. So now we can do this. We can measure a bunch of different FIR, impulse responses for a bunch of different models or knob settings. And then we can convert each of those into an IIR, and then we can look to see, is there a way to just kind of model that knob dependence, or maybe just store a whole bunch of these and interpolate between them. Storing a low order IIR system, storing hundreds of those or thousands of those is going to be easier to do than storing thousands of FIR filters, each with maybe hundreds or thousands or tens of thousands of coefficients. So this is the approach that we're focusing on right now. And we can do this two different ways. A time domain method where we can say, oh, I measured the impulse response and I'm trying to come up with a circuit or an IIR whose impulse response will pretty much mimic that measured impulse response. And there's two approaches that we'll talk about, and each of them has a MATLAB command, maybe in the signal processing toolbox. So if you don't have that, you might not be able to get to it. But one is called Prony's method, and that's based upon a method way back, developed way back in Fourier's time. Nope, he wasn't trying to come up with IIR filters, but he was solving a different problem, but the mathematics can be used to find modeling IIR filters. And then a improvement of that, which is called the time domain Steiglitz-McBride. So these are more recent researchers, maybe the 1960s, 1970s, heyday of the early DSP development. So two MATLAB commands will get you those. Now, you don't want to just blindly use MATLAB commands that you don't know what they're doing. You can get into a lot of trouble doing that. So we're going to go through how these things work so that you have some understanding of what's going on. And then there's also a frequency domain version of the Steiglitz-McBride. Oddly, this one is called Steiglitz-McBride, and this one has no reference in the name anyway to Steiglitz-McBride, but the basic idea is the same, or similar anyway. So we'll look at that, and there is a command available for that. Again, you might need to have the right toolbox to have access to that. So I'm going to go through a lot of the details of Prony because it's pretty well known and it's easy to characterize. Then I'm going to talk about how Steiglitz-McBride modified that to improve it. And then I'm just going to allude to how the inverse freq-z method works. So look, you can see what it's doing right there. freq-z takes IIR coefficients and gives you the frequency response, and Steiglitz-McBride is going to take frequency response values and give you the IIR coefficients. So it is kind of the reverse. So maybe not inverse is right, but reverse, perhaps. So let's talk about Prony's method. Like I said, there's a command for this. I say it's simple, but as in the case of most MATLAB commands, there's likely a variety of ways of calling it, and that can get you into trouble. Plus, you should know what it's doing and how it's working so that you can assess the validity of the results that you're going to get from it. So just an aside, you may, if you study DSP, you may run into the name Prony's method in a lot of different settings. It's a pretty general approach to solving a variety of different signal processing problems that are all slightly different, but all kind of related back to the same mathematical ideas. So here's what we're going to do. Suppose we have measured samples of an impulse response. So we take the circuit that we're interested in, we've got it in the lab, we apply our swept sinusoid to the input of it, we take the output of it, we do our inverse filtering technique that we talked about back in Unit 1, and we come up with values for the impulse response, discrete time values for those. Okay, so here's the idea, here's a picture. So here's the actual circuit who's got an H of S that we're interested in, and it has a corresponding impulse response, H of T. So I put a swept sinusoid into that system, and I do the inverse filter processing that we talked about. So remember, there's going to be a digital to analog converter here, and then an analog to digital converter here, and then we do our processing. So I'm leaving off some of the important boxes, but those are covered back in a note set in Unit 1. But nonetheless, we've measured this, and that should give us a good representation of that, assuming we've sampled everything reasonably well and so forth. Now, our job is to come up with a IIR filter model. So IIR is going to have a numerator and a denominator polynomial of Z. Now I put a hat on this so that we can distinguish its impulse response from the measured impulse response. And I'm just imagining if I had these polynomials and I put a delta function into it, it would create the impulse response of that. And in principle, I could imagine taking the difference between those two to create an error. And then my job is to adjust the coefficients in these polynomials to make this error small in some sense. So let's just write out those polynomials. So these are the coefficients that I would want to adjust to try to make these two impulse responses as similar as possible. So here's our mathematical formulation. Choose these coefficients to achieve this. I want to minimize over the choice of my coefficients the sum of the squares of the error. That's a least squares thing, right? Error squared sum. Well, that's a least squares, and this is called a least squares filter design problem. So we're trying to design a filter whose impulse response matches some, in general, some desired impulse response, but here some measured impulse response. And this is a hard problem to solve. It's what's known as a nonlinear least squares problem. It's not impossible to solve. It's just challenging. But we'll see, we'll allude to the more complete problem later on. But here's the cool thing. Prony's idea, way back in Fourier's time, so we're talking like the late 1700s, was solving a problem similar to this. Not exactly this, but was solving a problem similar to this and encountered this nonlinear least squares problem for a problem similar to this one, and said, I don't have access to computers back in 1700s, so I need to make this simple so I can do it by hand. And so he reformulated the problem, and this was the idea. So we still have this idea of having our model that we can ping with a delta function, and the thing that comes out, remember, we called h hat of n. And now we're going to run that through the same thing that we have down here. We're going to run it through here. So what does that do, right? A cascade of two transfer functions is the product. So this a of z is going to cancel with that. So really from here to here is just an FIR filter with numerator b of z and denominator 1. And so we know the impulse response of an FIR filter is just the sequence of the coefficients. So it would be these in sequence. And so that's what I'm showing here. B0 out to B sub P, and then zeros afterwards. So this is all thinking. We're not necessarily going to do all of what I'm saying here. This is our thought process. Now, similarly, I've left off all the stuff that I had out here before. We did that already in the lab. This is just sitting there on our computer. So now let's just think, starting with that. We're going to run that also through A of Z. That's the trick. So if this h hat of n and this h of n are both run through a of z, the idea is the things that come out should be similar as well. And so now we do a least squares problem on that. And that turns out to be a linear least squares problem, which is easier to solve. So what comes out here is going to be h of n convolved with, this looks like an FIR filter with the denominator of this playing the role of the numerator there. And so there's its impulse response. So the value here is h of n convolved with, so that's now convolved. On a previous slide, I think in the previous note set, I said that star in that scenario was multiplication. Here it is convolution. So I have a nice mathematical relationship between h of n, a of z coefficients, and ha of n. So I can write out what that is. So now here's the thing. This result needs to match that as best as possible. That's our new formulation for the problem. So we'd like it to equal this, but it's not going to equal it. And we can make it be as close as possible. So we can't actually choose the coefficients to give equality, but we can solve it in a least squares sense. So here's our new formulation. Choose the coefficients of our model so that if we minimize over the choice of those, this sum of squared errors, then those will be our choices for our model coefficients. Now the problem is, it's not a big problem, but the thing to keep in mind is that this change is only approximately equivalent to the original. So in other words, the solution to this problem isn't exactly the solution to the original nonlinear least squares problem, but it's close. And that was Prony's big idea. Prony could solve this. Prony could not solve the nonlinear least squares problem. So he reformulated it and said, close enough because I can solve it. Being able to solve it and get an approximate answer is better than knowing that here is what I have to solve to get the exact answer, but it's not something I can do. So that's the idea. So let's reformulate this idea here in terms of a matrix vector form. So I'm going to take some matrix H, which will hold the values of this. And I'm going to put these things into a vector and then say that, so the values in this resulting vector will be those values, and I'm going to at least set them in principle equal to the things that I'd like them to be. This is just a reformulation of a least squares problem. So we can't actually make that equal. What we're saying is I'd like it to be equal in the least squares sense. So some people will, not an 8 there, some people will actually put a least squares above. Equality in the least squares sense. So that's what we're after. But this is a standard way. If you've studied linear algebra, you probably did a least squares formulation like this. So now I'm just writing that out and showing you explicitly what's in the H matrix. So remember, this H matrix times the A has to mimic what this convolution is doing. So for every value of this, we're going to have one row of H interacting with the vector A. So here it is. So notice the rows. Each row is just shifted to the right. So that goes over there, and now H1 comes in. And now these go over there, and H2 comes in. So look, this is a flipped version of H marching to the right by right shifts. That's exactly what happens in convolution, right? Remember, discrete time convolution, you flip one and multiply it by the other one, and keep moving it forward to the, to the right. Each click gives you a new output. So we're going to start with this flipped. So the rest are over here. We can't really see them. They're out of view. And we're going to multiply this by that. So those will line up right here. Do that multiplication, do the addition, and it has to be equal to B0. That's the convolution idea. So, I mean, really it's actually equal to that H sub A thing, but we want it to be equal to B sub 0. So again, remember this is equality in the least squares sense. Then to get the next one, we shift forward. That's we flipped, shift, multiply, add, and get the number. So this is a matrix representation of this convolution. So that's the idea. And then we set it equal to the thing that we want it to be equal to in the least squares sense. Now we have all sorts of linear algebra machinery ready to go. But let's break this down into a couple different parts. So let's first look at the upper equations, because notice that this thing here has two different natures. Up here, it has to be equal to the actual coefficients that we're trying to pick. We don't know what those are, right? So here's the conundrum, right? For the upper part of this, I don't know these and I don't know these, and I just know those. So how do I solve something where I don't know things on each side? That's the hard part. It's like saying x is equal to 2y. Find x and y. They could be anything. So we don't really know. So how do we deal with that? Well, let's break it down into two parts. We have the part that's the conundrum. Those are the upper equations. Then we've got the bottom part, right? Once we get down to this row, these things fold over onto these, and they have to be equal to 0. Now suddenly we have something where there's just one unknown on a side. Well, I mean, there's more than one, but it's one entity on one side and everything else is fixed. That's the bottom equation. So we'll say all of this stuff times all of this stuff has to be equal to zeros. But we're going to do one other thing, right? So if we look at all of this times all of this, what do we see? We see a 1 times this vector, so that gives us that. And then if we define this to be a sub 1, it's multiplying just this part. So we'll call that h sub 2 gets multiplied into a1. And then those two things add to give 0. So there's the 0 that comes there. Now we're just going to say, swing this over to the other side. So now I get minus h1 is equal to this. So look, known, known, unknown. But again, this is solvable only in the least squares sense, because we can't really pick the a's to make this exactly equal to 0. We can just make it close to 0. And that's what solving this in the least squares sense would do. So we're going to solve that first. And that will be our solution to the a vector. Yeah, it's just really a1, but the only thing left is a 1. So once we know a1, we know all of a. Then we switch to this. I know this. I know this. There's no solution here. We're not finding something. We're operating to create the b. And that will be our b coefficients. And that's the trick. So how do we solve this problem in a least squares sense? Well, go to your linear algebra course, and you learned how to do that. You take the H2 matrix, you take its transpose times itself, you take the inverse of that times H2 transpose times the thing on the left. Oh, yeah, and there's the negative out in front because that was there. And that gives us the least squares solution. So I call that a sub 1 solution, but it's the least squares solution of that. Then plug that into here. Oh, So we tack a 1 on the top to get the A solution, which then gets mapped over into the B solution. So now we have all of our parts. Now, there are some problems here. Forming this matrix and then finding its inverse can be problematic numerically. Small numerical round-off errors and things like that can make matrix H2 what is known as ill-conditioned, and it makes the finding of this inverse challenging. It's sort of like looking at 1 over x when x is small. So if x is small and we have some small perturbation, it's going to make a big error, right? Look at 1 over x. So here's 1 over x, and here is x. And what is that? It looks like this. So this is inversion of a number. If we're looking at small x's down here, small values of x, there's the actual value, but any small deviation around that creates a big deviation in the result for 1 over x. So it's very sensitive to numerical issues. And so in the matrix setting, that's called ill-conditioned, and the matrix is said to be ill-conditioned. So we want to avoid that. And so there are ways to address that numerically. If you've studied linear algebra, maybe you learned some of these things, but you might have learned something called the QR decomposition. Its main use is in numerical linear algebra and used to address these kinds of ill-conditioning issues. So MATLAB does that with something called the left matrix divide. So it also does the QR decomposition explicitly if you want, but it has built into this left matrix divide the right way to do this with the QR decomposition. If you were going to try to code this elsewhere, you'd need to know how to do all this. But this is all done offline, so you can go into MATLAB, figure it out, and then carry your results over to your real-time implementation. So that'll give you the best possible solution. Just some notes on this left matrix divide. This is right out of the help command of MATLAB. So I'm going to you can read through that. I'm going to jump down to here where A is an m by n matrix, because that's the case that we have. And then it says here that A divided by B, left divided by B, gives the solution in the least squares sense from the QR decomposition with pivoting. So some further details and tricks for using the QR decomposition. So that does do what we want it to do. So we could do that. Now, I said there was a command for this called prony.m. There's a file in MATLAB. Again, you might need to have the right toolbox to get that. But prony.m implements this. And if you type help prony, if you have access to the prony command, it will spew out some things. And this is probably just part of that. But what we're going to do is put in our measured H here. And then what's this NB and NA? Those are our best guesses of the filter order, the numerator order and the denominator order, right? Because all the math we had up to now, we assumed we knew how many A coefficients and how many B coefficients. So what happens if we don't know that? Well, we know for our circuits it's going to be small. So we might just keep trying it with different choices, right? Second order, third order, fourth order, fifth order. Probably don't need to go much beyond that. And then just keep seeing how good your solution is. Check the least squares error for each and see. So that's how that works. Here's an example. I'm going to fit an IRR model to the impulse response of a Butterworth low-pass filter. So here we know exactly what it is that we're trying to model. So I run the Butterworth design. Gives me a discrete time filter. There's its actual coefficients. And now, instead of using a swept sinusoid to measure this, I'm going to just use the MATLAB command impulse z, imp z. So what that does is it says, okay, for those filter coefficients, this is the impulse response. And it has some, tricks in that it knows how long to compute that for, to get it, to show you enough of the values in the H vector until it decays down to some reasonable value. So now I've got the measured H. So I put measured in quotes here because I didn't really measure it. I just computed it directly. And now I'm going to try to guess the B and A from my measured impulse response. So I'm going to guess fourth order. I know from my previous commands that it is fourth order. So if I were to look at this B and A that come out, they are both 4 coefficients. So I put in my H, my measured H, I put in my assumed orders, and I run prony. Prony does all of the math that we just talked about. And so in this simple case, we would expect these to be exactly equal to those. And in fact, it does. So if you were to run this toy problem, you would see that you get exactly the right answer. Now, it turns out that prony is very, very sensitive to numerical errors or round off. So if there's any noise, now here we had a perfect measurement. That's why I put quotes measured. But this H here is really just an approximation of the actual impulse response, right? Because there might be noise from the ADCs and the DACs and the other electronics in there. So that H is going to be a little bit off. And prony is very sensitive to it. In fact, it's so sensitive that in a problem that I gave for homework in this course, I took an H from some designed filter. So I did this. I didn't tell the students what filter I used. And then I stored that H in a wave file so that the students could just read it in. But that was a wave file 16 bits per number. So I'm quantizing to 16 bits. That's a pretty fine quantization. And it turns out that prony gives wildly wrong answers. You had to go up to a really high order before you started getting a result that matched the original in terms of frequency response. So keep that in mind. Prony is good, but it's very, very sensitive to any kinds of errors. So maybe this is not the best way to do it. I thought I would just show you what's inside prony. So just setting up some things here, doing some zero padding, just getting all of the things set up right, doing some sort of check to make sure that our first value in the H vector is not 0, and then normalizing by that first value. It just makes things a little bit easier as long as we make sure that our H numbers aren't really big or really small. So that's all that thing is doing. And then this Toeplitz command, that's what they used inside this prony command. Toeplitz makes a matrix with a very specific structure. Down any diagonal, all the numbers are the same. And that, you can see that's kind of what we want here, right? If we go back to our H matrix, let me back off just a little bit more. See, down this diagonal, all H0. Down this diagonal, all H1. All of H2, and so on and so on. So every diagonal has the same number all the way down it. So that's what's known as a Toeplitz matrix. And if you call the command in MATLAB Toeplitz with the right things in, so our normalized H, and then a 1 and some zeros here. So these two things make this be a Toeplitz, or makes this give us a Toeplitz matrix that has exactly that H structure. And then you have to do a little bit of fussing here to get things right. I figured out that maybe they wrote this prony before they came up with their command conv MTX, which creates the convolution matrix directly. And maybe inside here is this Toeplitz command. I don't really know. But if you run this, you can replace all of that. It's not a big deal, but it's just a little cleaner. Plus, it's clear what it is that you're doing. So you don't have to change that, right? Because it's a command coming from MATLAB, and you might as well just leave it. But I mentioned that in passing. And then it just creates all the things, right? It creates the big H1, the little h1, the little h2. And then there's the left divide that creates the A1. And now we've got our A. And then we map that into the B, and we have to unnormalize by the C there. And so now we're done. And that's it. So that's how the prony command works. But remember, it's limited, especially if there's any errors in your measured impulse response, which in a real world setting, there's gonna be. So fortunately, there's Steiglitz-McBride method, which, you know, a couple centuries after prony came up with that. Steiglitz-McBride were innovators in the first wave of DSP development, and they said, hey, there's this prony's method, and maybe they played around with it and found out that it doesn't work so well in some situations. So they set out to improve it. And so they came up with an iterative approach. And so here's what they did. So assume we've got some initial guess or some current guess of what our A of Z is. So let's just call it A sub I minus 1. So I is our iteration index. So somehow we've been zooming in on the right A of Z, and that's where we are now. So I've got that, and now I want to use that together with our measured H to improve it and get a new A sub I and a new B sub I. So this was I minus 1, and I've updated it. That's the idea. Lots of engineering solutions are found this way. So let's now set up this scenario. So I've got this, and so I can imagine, I can figure out what H of n going through this IIR filter and this delta function going through this known IIR filter. And now I've got two things, a tilde and a hat. And I call them pre because they have been pre-processed by that. And now I'm just going to do this kind of thing. That's going to run through A of I. I need to find that so that if these two things are about the same, that means we've converged, then they don't do anything. And this thing should be approximately equal to that. And if indeed these two things are alike, this thing should be close to the true A. So that means this thing has the B over A structure. And so this thing should look like this, right? Remember, this just passes through because this is not there anymore. So that's the idea. So there's our iteration. So now we solve this problem. This is known from our current knowledge of that. And now we need to formulate this problem to solve for these. Well, that's just really kind of a similar solution, similar kind of setting that we had for prony. It's a little bit different, but it's basically the same. So here's what I was alluding to up here. When we've converged, then this and this should be approximately equal to A. They should be close to each other because our new iteration hasn't changed it much because we've converged. Those go away. And those two things should be approximately equal to A. And the new B sub I should be approximately equal to B of Z. That's the idea. So then we are really approximately solving the linear least squares, or the least squares problem that we want to solve. So that's the idea. So this is a pretty easy problem to solve. It involves forming matrix and vector forms for these things, similarly to how we did it for Prony. I'm not going to go into the details, but it's very, very similar. Solving with left matrix divide to give a linear least squares problem solution, and iteratively solving it. So that means we have to start with some place. How do we guess that? Well, inside this command, they literally just run Prony with some chosen P and some 0 there. And so that's how they do that. And here's an example. Again, this is a toy problem. We did this with Prony and it worked perfectly. We're going to do it again. I changed the order of my Butterworth to 6 now, but it's going to work perfectly for this toy problem. And as I said, Prony tends to be very sensitive to any errors in the measured H. So Steiglitz-McBride works a lot better. You could try redoing this example and taking this H here, write it out to a wave file and read it back in, and then run Prony and run Steiglitz-McBride. Don't check the impulse responses, check the frequency responses, and you'll see that Prony doesn't get it right until you boost the order up a lot. But Steiglitz-McBride gets it right with almost exactly the right order. So you can give that a try, play around with that. And then our third method, and you can see we're on our last slide, so I'm going to give very few details on this. I'm just going to outline the idea. But this is formulated in the frequency domain. So now we take measurements of the frequency response on some sample points. And then we solve this nonlinear least squares problem. So now instead of doing it in terms of impulse responses, this would be perhaps DFT values of our measured impulse response. And this would be the frequency response or the model polynomials evaluated in the frequency domain. But we are really getting those by adjusting the little b's and the little a's. So we could write this out in terms of the little b's, and we could write this out in terms of the little a's, and then we need to minimize this over the choices of the little a's and the little b's. And this turns out we're right back into a nonlinear least squares problem, but it's modern day. So we can solve this using nonlinear least squares problems, at least approximately solve it. And there's something called the Gauss-Newton approach. I think that's what's actually used inside the inverse freq command, but it is one of many approaches to solving a nonlinear least squares. There's a generalization of that called the Levenberg-Macart, and there's also a Newton-Raphson approach, I think is the name, to solving that. So there's a lot of different ways to do this. I don't remember off the top of my head what's actually inside inverse freq, but I think Gauss-Newton or maybe Levenberg-Macart. We will talk about Gauss-Newton and Levenberg-Macart at the end of this unit for solving a different problem. So here is our little toy problem, and that gives, again, the exact answer. How sensitive is this to round off? I don't have experience with that, to be honest, but I would expect it to not have as much sensitivity as Prony does, only because it's solving the full nonlinear least squares, which is an iterative approach. So anyway, you need to find a model for a linear stage inside a nonlinear device, overall nonlinear, guitar amp, distortion overdrive box, fuzz box, whatever. If there's a linear stage in there that you want to figure out how do I implement that stage, these are good methods to do that. Okay, so the rest of this unit will just continue progressing through these ideas, getting into more and more advanced and more recent approaches to coming up with discrete time models for guitar amps and overdrives and things like that. So I hope to see you in the next video.